So we were saying that now we will evaluate slope again at t half y half, okay? Because we already found k2, okay? Because once you find y 1/2, or here ti y at I plus 1/2, then you will be ready to find the corresponding slope. And once you find the slope, you will go back to this point, okay, and draw a line of slope k2. So now we were in this step. We went back to point 1, and we take a line of slope k2, okay, and this line will intersect, will give us a correction of the midpoint. So now we will compute what a new value of y I plus half. So this is a corrected value. We can call it y I plus half 1. So now we will say that the updated value of y half is y0 plus h over 2 k2, because we are moving with the slope k2, a distance of h over 2. We'll get the updated value of y half here. And then once we get y half, we will be ready to compute what is k3 at y half. So all we have to do then is to evaluate y prime as t half y half. So just we have to update, to put the update of y half, and of course t1/2 is still 0.5, while y half was corrected, so we use the correction, and then we get the value of k3. Once we get k3, then we go back to the first point, but now we will move a step of h instead of moving a step of h over 2. This will allow us to find y1, okay? So y1 is y0 plus h k3, and we can evaluate now at this y1 what is the slope k4, where k4 is defined as ft1 y1. In this way, we proceeded just the first time step from 0 to 1. We got 4 coefficients k1, k2, k3, k4. So now we can find an estimate for these 4 coefficients. So our phi now will be calculated as 1 over 6 k1 plus 2k2 plus 2k3 plus k4. Once I update my phi, I should not forget to update y1, okay? Because the final y1 that I will calculate will use the following phi, not k3, okay? Pay attention. So here's the value you did when you evaluate y1. Here you used k3. This evaluation was just used in order to compute what is k4. But this is not the final value of y1. You just use this evaluation of y1 to get k4. But once you have k4, you can find the mean value of phi using the weighted average between k1, k2, k3, and k4. Once this is done, I can find my final updated value for y1 by saying that I advance one time step from t0 to t1, and I write that y1 is y0 plus phi times h, and I get my y1. This is the end of the first time step. I should repeat this procedure for each time step, for time step 2, 3, and 4. So of course it will take time, but it is worth because the accuracy of Runge-Kutta method is very large. It's a method of order 4, and we call it, this is why we call it the RK4 method. Okay. So now, again, in step 2, same procedure, but now my interval, instead of being from 0 to 1, my interval is from 1 to 2. So the midpoint, okay, here will be 1.5. So I evaluate first y at 1 plus half, so y at 1.5, which will be y1, which I evaluated in the previous step, times h over 2 k1. K1 now is the slope at y1. So before being able to do this step, I should calculate k1, which is just ft1 y1. T1 is 1. Y1 is the value I obtained at the end of the first step. So this is y1 that I will use, 6.2012. Okay. Now I have that t1 is 1 and y1 is 6.2010. So k1 I can evaluate it by just saying that I will replace in this equation y prime at 0.1 is 4 exponential 0.8 t1, which is 1 second, minus 0.5 y1, and y1 is the value I obtained at the end of the first step. Okay, so now the remaining procedure is the same. I will, once I find k1, I find y1 plus half. Then, once I find y1 plus half, I evaluate the slope at it. This represents k2 of the second step. Once I find k2, I go back to the initial point, and now I draw a line of slope k2, so I can update y1 plus half. I can find a new estimate for y1 plus half. This will allow me, once I find it, to compute k3, which is the slope at the corrected value of the midpoint. And then once I get x3, I go from t1 to t2. So I go a step h to evaluate y2. And this is not the final evaluation of y2. I just use it to compute k4 at t2, y2. Once I get k4, I will update y2 by finding now the mean slope as weighted average of k1, k2, k3, k4, of course, in the second step. And then I will be able to find the final value of y2 by using the mean phi coefficient, which is the weighted average of k1, k2, k3, and k4. So now I updated y2. I'm done with the second step. I will repeat the same procedure. So please try to repeat the procedure to calculate y3 and y4 to make sure that you understood well the math. Okay, so now if we want to have an overview of what we did, we repeated the same problem using several methods. First, we used Euler method. Then, if you do Huygens method without correction, this is what you obtain. If you do Huygens method with a stopping criterion of 2%, this is what you obtain. If you use the midpoint method, this is what you obtain. And if you use the RK4 method, this is your results. So you can estimate the true relative error for the different methods. As you can see, the worst result we got them with Euler because it is expected since it's a first order method. Both the Huygens and midpoint methods are second order methods. But you can see that as you increase the number of corrections, so by using more corrections, you can have better values. So here, in the example we did corrections until having relative error between corrections. Approximate error is 2%. If you want to get better results, you should put a stricter criterion. Now, what is nice about the midpoint method is that it provides an error of same, or it has the same order of a Huygens method. Both are methods of order 2, but midpoint method without correction will give me a very good result. So in one step, I get a very acceptable result. And of course, RK4 will be the most efficient because it's a fourth order method, but also as computational time, you can see that the midpoint will require the less time and will give acceptable results. Now, until now, we have just considered a single differential equation. What if we have a system of differential equation? How to deal with this? So if I have a set of differential equations to solve in parallel, what can I do? It's very simple. I just proceed for all variables. I update them step by step. Okay. So I will give you an example. You will, in a way that you understand the idea. So if we want to solve for the velocity and position of the free falling bungee jumper using Euler's method. So here they gave us two differential equations: dx by dt equals to v, and dv by dt equals to g minus cd over mv squared. Okay. Now you have x is the vertical distance from the plate, and v represents the jumper free fall velocity. And we want to integrate these relations from 0 to 10 seconds. And we are using a time step of 2 seconds. So what do we do in this case? All we have to do is to uh, to solve step by step for v and x. Okay. So we have the initial conditions for both. So we know that for x t equals 0 and x0 equals to 0, and for v at t equals 0 v0 is equal to 0. Okay. So now all we have to do is to update at each time step these values. So you can keep the order of the equations. So here you have the first relation is dx by dt. The second relation is dv by dt. Okay. Now, to compute the slope for the x equation, you start by saying that uh, dx by dt is equal to v. So I will start with the Euler method. I will start by the slope at the first point. Okay, so I consider that my initial slope between interval 0, 1 is equal to the velocity at the first point. So it's v0 equals to 0. And now, once I find the value of phi x, I can advance one time step in x to go from x0 to x1. So I say that x1 is equal to x0 plus phi x times h, which is 0 plus 0 times 2, it's 0. And of course, this is not true, and you can know already that this is not true because, and why we have this error here, because you are using Euler method. You are considering that the velocity in the interval 0 to 1 is just equal to the slope at 0, which is 0. Actually, the velocity is varying, okay? And what is happening is that uh, x will be different than 0 at 1. But this error is due to the method used here, which is Euler. Because Euler method consists of taking the mean of the slope equal to the slope at the first point of the interval. This is why we induced a high error in the first estimate, because it seems that the bungee jumper is not moving while it is. So if you use the other methods, if you use instead of Euler, you use Huygens or midpoint or RK4, of course you will get x1 different than 0, which is more accurate. Okay. Now we will proceed with V equation. So all we have to do then is to update V. So to update V, you have the slope at V is G minus CD over MV0 square equals to 9.81. So if you advance one time step from V0 to V1, you say that V1 is V0 plus the slope you got from Euler approximation, which considers that the slope is equal to the slope at the beginning point, which is here of the interval, and here which is 0, because the first interval is from 0 to 1. So we evaluate the slope at 0. The slope phi v is g minus cd over mv0 square. So we evaluated it's 9.81. So we get an updated value for v1. And now, so as you can see, just when we have a system of equations, we should update the different variables in the first step. And you find what is x1 and you find what is v1 using the method they asked you for. They can ask for Euler, they can ask for Huygens, for midpoint, for RK4. All of them can be applied, but now you should apply them not on just one equation, on two equations. So you should update the two variables before being able to move to the next step. So now, once you know what is x1 and v1, you can move to the next step. For the next step, again, you repeat the same procedure. I start with my first equation. I should compute dx by dt, which is now at point, I consider that the slope, now my interval is 1 to 2. If I use Euler, then the slope I will use is the one at point 1, which is v1. So phi x equals to v1 equals to 19.62. Now I will advance one time step in x from x0 to x1. So I will say that, sorry, here it's from x1 to x2. So if I advance from x1 to x2, I write that x2 using Euler formula. x2 is x1 plus phi x computed at point 1, okay, times h. So I get my x2. I will do the same procedure now to compute v2. I should find the slope v at v, the slope dv by dt by replacing in v prime equation, which is the second equation I have. If I replace in v prime, I will replace now v by v1, because I consider now that the slope is, that should be evaluated should be at point 1. okay, which is the beginning point of my updated interval. So I get that V2 is V1 plus slope I found times the step size h. I get V2. And I will proceed. So I will continue to do the same procedure for all other time steps. So I can update my values at different times. Now, the purpose of this table here is to show you the comparison of results between Euler and RK4 method. And you can also develop your own tables for Huygens and midpoint methods. So you can see, again, you can have the same conclusions that, of course, RK4 will give you much better results. Okay. And you have here, in Euler method, you will induce high relative error for position because of what I told you. And here you are taking the slope at the first point is a bad way. And this will lead to high error, especially in position, because it seems that you are not advancing in the first time step because you are considering that between 0 and 1, the velocity is equal to velocity at 1, which is 0, which is not true. Okay, this is why, because other methods will take a slope that is closer to the actual mean between T1 and Ti and Ti plus 1. With other methods, you will end up with much lower errors for X. Okay. Even, you can see that in Euler method, the relative error for X was much higher than the relative error for V, while when using RK4, it is the inverse, because already you were able to fix this issue that you are not considering just the slope as the first point, you are taking a much better estimate of the mean. So as you can see here, I can achieve very small errors using RK4, while with Euler method, I have very large error. So for Euler method, what can I do? What do you suggest in Euler method to enhance the predictions?
Decrease the H.
Exactly, I can decrease the H. While for RK4, even with large H, I am fine. Okay, so it's true that RK4 will involve more computational time, but on the other hand, if you want to obtain the same accuracy, no, it's much better, because here you need to take much more smaller step sizes, and then you should repeat the procedure several times. So at the end, you will save time in this way, because here you will, if you want to get the same accuracy, you will reduce a lot H. So you have to do a lot of computations in order. You should, if you want to vary the step to get the same relative error, true error. Okay. Now,
دكتور
yes,
ممكن الميد إذا استعملناه هون ما it does require less computation than ال RK4.
اكيد it requires less. هلا الايرور ما حتكون هالقد واطيه، بس at least بتكون acceptable. Okay, انت you should always compromise between accuracy and computational time. So already ال RK4 ليك شو عطتك errors صغار. So if you tolerate let's say 0.1% true relative true error، ما في لزوم تروح على RK4. You can just go for the midpoint. يمكن it can achieve for you this error, an error of order of 0.1% with a lower computational time.
Yes.
Okay. Now, until now, we have considered first order differential equations. But what will happen if we have a higher order differential equation? How we can deal with this? Since we develop techniques to solve a first order differential equation, we will try to transform a certain higher order differential equation into a system of linear equations. And this is a very simple technique. It consists of the following. For example, if you take the Newton's second law, sum of forces equal ma, which is m times second derivative of x with respect to time, it's a second order differential equation. We will try to convert it to two first order equation. How to do this is very simple. I just say that the second derivative of x with respect to time is the first derivative d by dt of the first derivative. So it's d by dt of dx by dt. And then I say I will say that this is function v, this is the velocity function. Okay. So now instead of having one second order differential equation, I can replace it by two first order linear equations. The first one is v equals dx by dt. And the second one is, if I replace in this equation dx by dt by v, I will get that f is equal to m times dv by dt. Okay, that's it. So now I transformed my equation from a second order to a first order equation, but instead of having one equation, I have two. And you can generalize this. So if I have a third order differential equation, I will transform it to three first order equations. And since I know how to solve this system, then I can solve for my differential equation, whatever is the order of it. I just have to transform it to a system of first order differential equations. Now, of course, higher is the order, it will be more complex, but we'll do some examples so it's easy. Let's say if we start from this example, so that f is equal to m second derivative of x with respect to time, and always if you have a first order equation, they gave you one boundary condition. If you have two order differential equations, they will give you two boundary conditions, one for x and one for dx by dt. Okay, so since you have two conditions here, this will allow you to solve a system of two first order differential equation, because each first order differential equation requires one boundary condition. So I will transform this system from the following form to a system of two first order equations with one boundary condition for each. Okay, and now we have already solved one problem that is similar to this one, consisting of two linear equations. So all I have to do is to proceed at each time step. I solve, let's say, I know at t equals 0, v0, x0. At t1, I evaluate v1. I evaluate x1 based on the method they asked me for. Once I update them, I move to t2. I evaluate v2. So it's dependently, I can evaluate them because at each step, I will use the values from the previous step. Okay. So now, let us take an example using a higher order, a third order differential equation. So I want to transform the third order differential equation given into a system of three first order differential equations. The initial conditions given, so since it's a third order system, they will give you three boundary conditions. They will give you y0, y prime 0, and y second 0. So the whole idea here is to do a certain transformation of variables to allow me to write this equation of third order into a set of three equations of first order. How to do this? So here in this equation you have y, third derivative of y equals to t minus y. Okay, so my variable here is y and time. And I want to include derivatives of y. In order to go from y to y third, I did three derivatives. So I need one variable for y prime. So let's say I define the first variable y prime as g. Okay. My second variable of interest will be y second. But what is nice here, that y second is what? Y second is the derivative of y prime. So is the derivative of g. So I can write, instead of z equal to y second, I can write it as g prime. So the purpose is just to use first order derivatives without second and third order derivatives. Okay? And now I am interested in y third. Okay? What is y third? The third derivative of y. The third derivative of y is simply the derivative of y second, which is z prime. So all I have to do now is to say that if I define the two variables g and z as g equal to y prime and z equal to y second, then I can say that the third derivative is simply the second derivative of g or the first derivative of z. Okay, and z, which is y second, can be written as the first derivative of g. By doing so, now what are the three equations involved in my system? First, I have this differential equation, which will remain as it is, but I will replace y third by its value, which is a first derivative. I will not use g second because it's a second derivative. I will use the variable which the first derivative of it will give me y third, which is z prime. So my first equation will be the first derivative of z equals to t minus 1. Now what are my two other equations? Just the change of variables I did. So I defined g as y prime and I defined z as g prime. So as you can see, I don't see any derivative of order 2 or order 3 in this system. All my derivatives are first order. In this way, I have transformed a third order differential equation into a system of 3 first order equations. And once this step is done, then all I have to do is to solve in the way we have done with previous problem. So all I have to do, depending on the methods they gave me, Euler or Hunes or midpoint or RK4, whatever is the method, the same procedure. I update at each step. I update the values for my three functions. So now I have initial conditions because they gave me in the problem what is y0. So here the condition of is known, the boundary condition. For g prime equals to z, I will use the condition g at 0, and g is nothing than y prime. G is equal to y prime. So I can replace g by y prime, g at 0 by y prime at 0, and y prime at 0 is given to be 2. So g at 0 is 2. And finally, for the first equation, I need a boundary condition for z. Z at 0, z is g prime, and g prime is y second. So I replace z at 0 by y second at 0, and y second at 0 is 0.5. So now, once I know the boundary conditions for these three equations, all I have to do is to, depending on the method used, I will proceed. So I will evaluate now at time step. If I'm using Euler method and my step is 1, I will evaluate at t equal 1 what is z1, then at t equal 1 what is g1, and what is y1. Once I'm done with the first step, I move then to the second step, and I repeat this procedure until I'm done. Okay?
دكتور
Yes.
تقريبا كم step بدك 3 equations؟
What do you mean by come step?
يعني إذا مثلا الانترفل من 0 ل 2
I will tell you what is H, Hassan. I will tell you what step to use. أنا قد هطلب maximum بطلب منكم 2-3 iterations, not more.
كيف يعني 2-3 iteration؟
يعني أنا بطلب منك مثلا مش إنه ك time step قصدي. يعني أنا بقول لك integrate between 0 and 3 with a time step of 1. يعني you should evaluate at 1, at 2, and at 3. يعني at t equal 1, what is the values of z, g, and y? At t equal 2, what are the values? At t equal 3, what are the values? إذا عم تعمل Euler method ما في iteration بقلب التايم step. إذا طلبت منك use Hume's method, let's say with 3 correction، ساعتها كل variable كل ما بدك تعمل update هون بدك تعمل 3 corrections. بال t1 للz بدك تعمل 3 correction، للg بدك تعمل 3 correction، للy بدك تعمل 3 corrections. It depends on the question. شو طلبوا منك تعمل؟
يس دكتور، بس إذا هيك يعني ما بدها تاخد وقت، لأنه أنا عم بعمل الشغل على 3 مرات ارجع انتقل
اكيد
على
هلا ما انا اكيد ما حاطلب منك كثير، يعني مش حطلبك، مش هيك عملنا Euler هون just تشوفوا الواي to apply it. اكيد it will take time، بس بالاكزام ينطلب منك شيء you can finish it اكيد.
اوكي دكتور.
اوكي يعني مثلا يمكن ما اطلب انا الميد بوينت، يمكن اطلب منك الميد بوينت ميثود هون لانه it's easy to do. لو عدت ل 3 variables it's fine. أو يمكن
Yes,
أعطيك
طبعا.
ساعتها system that is simple، أو أطلب منك to just compute at one time step مش at several، يعني بس at T1 مثلا.
يس لانه انا عم بحسب مثلا RK4 يعني اذا بدي اعيدها لكل
Yes,
وحده.
yes, of course. Look, بالنسبة للtime I will take of course in consideration. لو بعطي time قصير بس مش حاطي impossible يعني أكيد. I don't give impossible times لأنه في كتير عم بخلصوا بالexams، بس إنه أكيد they are fast. And this is why I am doing arrays after to consider إنه مش كل العالم كتير سريع.
يس ميرسي دكتور.
Okay. Any other question? So we are done. This is the end of chapter 22. Please, for tomorrow, as I told you, I have a vaccine, so we will just postpone the class to 5. So I will answer, prepare your questions if you have any questions for the exam. I will answer questions, and if we can do review on problems that you want. So that Thursday we correct the homework, okay? Thursday, Friday we correct the homework.
دكتور
As revision for the exam, yes.
بكره يعني تعمل اكسرسايز على chapter 15.
على اللي بدكم اياه، yes على chapter 15 او اذا
لأنه-
حيلا يعني اذا حيلا chapter عايزين فينا نعمل practice اكثر we can do it.
Okay doctor, thank you.
Okay. Any other question before we start? Okay, bye bye.